Hi everyone. In the last video, we defined the heat capacity, which is an object that tells us how hard it is to heat up a system. In other words, how much energy we need to add in order to increase the system's temperature. And we argued that the heat capacity along a curve R, which say fixes coordinates a1 through an minus 1, was equal to T times the partial derivative of s with respect to t while fixing all of those coordinates that I mentioned, a1 through an minus 1. Excellent. So where a1 through an minus 1 are fixed on R. Good. Now, what we'd like to do today is just give some examples of heat capacities. The first examples are, maybe unsurprisingly, for the ideal gas. And today we'll do both the monatomic and diatomic cases, even though typically we've just done the monatomic case. Okay, so remember that the entropy for the ideal gas is nkb times the log of sigma v over n, u over n, to the, in the past I've used the letter small a to denote this, and then plus a plus 1 times nkb. So for the monatomic case, we had a is equal to 3 halves, and for the diatomic case, we had a is equal to 5 halves. Good. Okay, so let's get to it, and first we'll try to find CV. Okay, so what coordinate system should we work in? We want our curve R, and notice that there's actually a difference in notation here. Here I'm saying for fixed V. So we want to fix V and N, and then we need to take a derivative with respect to T. So we should work in coordinate system T, V, N. All right, good. Now let's rewrite the Sackur-Tetroda equation in this coordinate system. That would mean we get S is equal to nkb times log sigma V over N, and then we need to trade out U for N and T. We've done that a bunch of times, so I'm just going to skip to it. We get, oh, not 3 halves, but A times kbt to the A, sorry, plus A plus 1 nkb. Good. All right, so now let's take our derivative. So we get that CV should be equal to T times the derivative with respect to T of all of this stuff, fixing N and V, and we've done this calculation also a lot of times, so this will be T times nkb from this nkb here, times the derivative of log of t to the a. Log of t to the a has derivative a times 1 over t. All right, so we get, at long last, a times nkb. Good. Now, we had mentioned in the last video that CV can also be computed in a slightly different way. Because t is the partial of, well, I should say t inverse. Let's back up a little bit. T inverse is equal to partial u of s, fixing n and v. And then by the inverse function theorem that we learned about a couple of videos ago, that implies that t is equal to the partial with respect to s of u while fixing n and v. Good. Now let's stick that in here. That implies that CV is equal to partial s of u fixing n and v partial T of S fixing N and V. And maybe if we move the order around here, this actually becomes a little bit clearer. This is, in fact, the version of the chain rule that we also gave in Lecture 7. So we have an S here having its derivative taken, and an S here being the thing with which we're taking the derivative. And we also have the same two fixed coordinates, which means that this is exactly equal to the partial with respect to t of u while fixing n and v. So let's check. Remember that for the ideal gas, we have that u is equal to A times n kb t. We've covered this quite a lot of times. Well, then that implies pretty clearly that CV is equal to just A times n kb since we're taking a t derivative. Good. And as expected, these two answers match. Oops. There we go. All right, now let's find CP. Okay, so CP is equal to T times the partial with respect to T of S while fixing P and N. Good. So what coordinate system should we work in? Well, we have T being the thing with respect to which we're taking the derivative, and then we have P and N. So this implies coordinate system T, P, N. Excellent. All right, so now let's rewrite the Sackur-Tetroda equation in that coordinate system. So now we can't use V over N. We'll need to replace V with P, T, and N. And to do that, we'll just use the ideal gas law. Recall that the ideal gas law is the same for the monatomic and diatomic versions of the ideal gas. So we get PV is equal to N kBT, or V is equal to N kBT over P. Excellent. So now we have V over N, which we can rewrite as kBT over P, since the N up here got divided by the N that was in the denominator here. Excellent. Next, we have U over N, but we need to make the same replacement that we made up here in terms of A kBT. So we get A kBT to the power A plus A plus 1 N kV. Excellent. Now, when we take the t derivative here, we need to note that there's one more power of t here. So we have altogether, if we multiply all of these, t to the a plus 1 inside of the log. So when we take our t derivative, we'll get nkb times a plus 1 times the times 1 over t. So the derivative of the log of t. Good. And canceling out the t's, we once again get something that is t independent. So a plus 1 times nkb. All right. And that's maybe something I should have pointed out a little bit more clearly already when we did CV. The ideal gas has a constant heat capacity at constant volume and a constant heat capacity at constant pressure. Now, often we'll talk about the heat capacity ratio, gamma. So we'll define gamma the heat capacity ratio by gamma is equal to CV over CT. And sorry, actually, it's the uh, inverse of that. So it's Cp over Cv. So for the ideal gas, gamma is equal to A plus 1 times NKB over A times NKB, or A plus 1 over A. Good. Let's figure it out in the two cases. So for the monatomic ideal gas, A is 3 halves, so we get 5 halves over, let me make sure that it's clear that this is gamma. 5 halves over 3 halves, or 5/3. And for the diatomic ideal gas, gamma is equal to 7 halves over 5 halves, or 7/5. Now, the reason that we define this is that we can measure heat capacities relatively easily. So the way that we would actually measure one is to have a fixed box of gas. And in the first case, we would have this gas at constant volume. And in the second, we would have it at constant pressure. And maybe we would do that by placing a piston on one side of the box and applying a constant force to the piston such that it had a constant pressure given its known area. Good. Then we would start adding heat to the box. And we could do that by adding in a heat source here somewhere. And we could measure its temperature. So we could have a little thermometer in here. And some sort of heat source over here. So heat capacity is one of the easier quantities to actually measure. And similarly, the heat capacity ratio is something that we can easily derive just by getting these two heat capacities. And it actually tells us a reasonably large amount of information about the gas that we're working with. So we can define this kind of ratio for any type of gas system, not just the ideal gas. All right, let's do one more example of heat capacities before we break here. And that's for the Einstein solid. All right. Well, let's first remember what the energy of the Einstein solid was as a function of n and t. We had that this was equal to 3n u naught times 1 over e to the u naught over kBt minus 1. Excellent. Now, in this case, we only have one sort of easy thing to fix, which is n. So we'll just say c, because we have no fixed volume in this case. So what we would just get is the derivative with respect to u while fixing n. The derivative with respect to of u with respect to t, sorry, while fixing n, which is going to be equal to 3n times u naught times the derivative of this thing. And it looks kind of gross, but we can do it relatively easily. All right, so imagine that this has a is just raised to the power of -1. So what happens is we pull a negative 1 down. And then that's raised to the minus 2. Next, we need to take the derivative of this inside part, which is like the derivative of this e part, and then the derivative of minus 1. But the derivative of minus 1 is 0. So we just have to worry about the derivative of the e part. Imagining that this is like e to some function of t, we'll get e to that function times the derivative of the function. All right, so what's the derivative of just this function here? Well, that is going to be minus u naught over kb, since those are constants, times t to the minus 2, since t was to the minus 1 here. Okay, good. So now we can put all of this together. 3n u naught, and actually let me break this up into numerator and denominator. So let's do the numerator first. We get this minus sign canceling this minus sign in the numerator. And we'll get 3n u naught squared times e to the u naught over kbt. Oops. And in the denominator, we get kbt squared from this and this times e to the u naught over kbt minus 1 quantity squared. We can check this expression by making sure that it has the right type. What is the type of heat capacity? Well, if C in general is T times a derivative with respect to T of entropy while fixing some coordinates, then this T's type and this T's type in the denominator cancel. And we see that heat capacity has type energy. Good. Okay, so let's check that that is true for this expression. We have n, which is typeless. Now we have u naught squared here. And if we turn this into a kbt or a kb squared here, we can pull a kb out to the left. Then this u naught squared and kbt squared in the denominator cancel because they both have type energy squared. Both of these expressions involving the exponential have no type, and so we do have something with the correct type of entropy. Good. So now let's try and think about what this expression does. Once again, we need to think about the limits. We already know that the low temperature limit for the Einstein solid is not particularly empirically accurate. So let's worry mostly about the high temperature limit. In the high temperature limit, we should be able to get a result. Now, I won't go through this carefully because I think that it is not particularly useful for me to do so, and because I think that we can just use our high temperature expression for the energy in order to get an answer. Recall that the high temperature energy was U is equal to 3N kBT plus a constant. And that means that when we take this derivative with respect to t, we get 3 nkb. I invite you to go and check this limit carefully, that this expression has a limit and that it's this. You can use L'Hopital's rule at least one time in order to figure that out. So once again, we have a high energy heat capacity which does not depend on temperature. And this is in fact an important empirical result that was found in the 19th century, which is usually given the name Dulong-Petit law. This is in fact the way that the Einstein model was to some extent empirically verified, because it predicts the Dulong-Petit law at high temperature. That's all I had to say about these examples. I'm going to release a supplement video after this where we justify the idea that Cp is greater than Cv most of the time for all sort of regular examples. Until that video, I thank you so much for watching. Bye-bye.